This is Chapter 6, Section 4, Problem number 7. So these are first-order linear differential equations. Problem number 7, is that what I'm doing? 7 is our first example. So we have y prime minus y is equal to 10. So when we have first-order linear differential equations, we're going to use integrating factors to solve it. So we have to put the equation in standard form, which has the form y prime plus p of x times y is equal to q of x. So first we have to know whether it's a linear differential equation. And it is, because we don't have any y squareds or y prime squareds, so they're all just first order. And so linear first order means you just have one first derivative. You don't have a second derivative. So, and then it is a first order linear differential equation. Then you have to put it in standard form, which is like this, and you can see it is already in that form because there's no coefficient in front of y prime. So this is standard form. The next thing we do is we identify p of x and q of x. So p of x is equal to -1, and q of x is equal to 10. Okay. Now we calculate the integrating factor, and the integrating factor we'll call u of x, and it's equal to e to the integral of p of x dx. So p of x is -1, so we get u of x is equal to e to the integral of -1 dx. So you factor out the -1, integral of dx is x, so we get e to the minus x. So that's u of x. So the way we've learned in class is we take the original equation and we multiply it by the integrating factor. So we multiply everything. So I'm just going to put the original equation in parentheses and have the integrating factor multiplied by everything. So what that gives us is e to the minus x y prime minus e to the minus x y is equal to 10 times e to the minus x. Now, because we chose the integrating factor through this method, what we're able to do is to take these two terms and combine them, because this is a result of a product rule differentiation. So, well, the one term is this, and the second term is that. So what we do is we say that is equal to e to the minus x times y prime. And so we're taking the derivative of a product, and if we take the derivative of that product, we take the first term times the derivative of the second, which is what we get here, times the derivative of the derivative of the first, which is going to be minus e to the minus x, which is this, times the second term. So you see it works out. And then what we do is we're going to integrate both sides. So basically we have the integral of e to the minus x y prime, and we're going to multiply that by dx. We're going to multiply the right-hand side by dx as well. And so the result is always just the term in the parentheses. So you get e to the minus x times y is equal to the integral of 10e to the minus x dx. So then we just go through this integration. So we factor out the constant. And we know what the integral of e to the x is. It's e to the x. But what is the integral of e to the minus x? Well, it's minus e to the minus x. That's an easy answer. But if we let u equal, which is a different u than what we're talking about, this is the u for substitution. If we let u equal negative x, then du is equal to negative dx, or dx is equal to negative du. So we can make that substitution. So we get 10 times the integral of e to the u times negative du. So for dx I put in negative du, for minus x I put in u, so then you can integrate it. So you'll have 10, there's a negative sign comes from here, so you factor that out. So you have negative 10 times the integral of e to the u du, and that's something that is in the book formula, so we integrate that and you get negative 10 e to the u plus c. The right hand side is e to the minus x times y. And then we substitute u back in, so we get e to the minus x y is equal to negative 10 e to the minus x plus c. And then we want to finally get y by itself, so we divide by e to the minus x, divided by e to the minus x, divided by e to the minus x. So we're dividing everything by the same number, the same quantity, so these cancel out, and you end up with y is equal to, and these cancel out, negative 10 plus c over e to the x, which I would probably change that so the negative number is second. So I get e to the x minus 10. Okay, so that's my answer, and I'm sticking to it. But I'm going to look in the answer book to make sure that I didn't mess anything up. So this is the first one in for a few minutes. I have to look it up. Number 7. Negative 10 plus c e to the, let's say e to the x. Oh, okay. Actually, this is e to the minus x here, so I did make a mistake. E to the minus x. So I can rewrite this as y is equal to c times e to the x. By moving this to the numerator, I change it from a negative exponent to positive exponent. So that's the final answer. Okay. Okay, so now we're going to do another first order linear equation. Basically the same procedure. So this is problem number 9. So let's write it down. Y plus 1 cosine of x dx minus dy is equal to 0. So I think we're going to divide everything by dx to get it into a form that involves dy dx. And I'm just going to, and then I'll replace dy dx with y prime. This is the case, these are cases where y prime is really easier to deal with. Okay, so we have dy dx. So then we will call dy dx y prime. And now we need to put it in standard form. So let's multiply everything by negative 1. So everything changes sign. And this part is not in standard form yet because we have y plus something. We don't have y times something by itself. So what we would do is we would multiply these out, so you get negative y. Well, let's put the cosine of theta first here. So, cosine of x. So we have cosine of x, y. And then the second term is this negative 1 times the cosine of x. So when you move that to the right-hand side, it becomes positive. So you'd have positive cosine of x. Okay, so now it's in standard form. There's no coefficient in front of there. There's we have y prime and y. It's first order. It's linear because we don't have y squared or y prime squared. So we can identify p of x. We don't really need to identify q of x, to be honest. Okay, so p of x is minus cosine of x. So we're going to figure out what the integrating factor is, and it's equal to e to the integral of p of x dx. So p of x is negative cosine of x. So we have e to the minus, well, I'm sorry, e to the integral of negative cosine of x dx. So the integral of the cosine is the sine, and we'll have a negative sign. So it'll be u of x is equal to e to the minus sine of x. No, we don't have to have dx in there. So the integral of cosine of x dx is sine of x. They have a negative sign. So that's the result. So once we do that, then we go back to the equation standard form, and we multiply everything by the integrating factor. So let's just show that explicitly. Again, multiply that by everything. So when we do that operation, we'll get e to the minus sine of x y prime minus cosine of x e to the minus sine of x times y. And that's going to be equal to cosine of x times e to the minus sine of x. Now, because of the way we chose the integrating factor, this can be collapsed into this product, which is this term, e to the minus sine of x, and then the y part. And then we do a prime to the quantity. And so when we take the derivative, we get y prime times this, which is the first term. If you take the derivative of e to the minus sine of x, you get e to the minus sine of x times the derivative of the numerator of the exponent, which is the derivative of the sine is minus the cosine. So you get minus cosine e to the minus sine of x. So that's the second part. So we can do that. You don't have to do that. Just as long as you do that part right, you don't have to convince yourself. So then we can integrate both sides. So we have e to the minus sine of x y prime times dx is equal to the integral of the cosine of x e to the minus sine of x dx. And the integral of this is just the term in the parentheses. And the right-hand side, we just have to integrate it. It may look complicated, but it's not as bad as it seems. Because what we do, again, using u substitution, we would let u equal negative the sine of x. So du would be equal to, well, the derivative of the sine is a cosine, so you get negative cosine of x dx. And what do we have? Cosine of x dx. So we can say the cosine of x dx is equal to negative du. So then we make the u substitution into this to the right-hand side. So let's just do that for right now. So we'd get the integral of e to the u times du, or times dx, but dx, or cosine of x dx is minus du. So we factor out the negative sign. The integral of e to the u du is just e to the u plus our arbitrary constant c. Okay, then we plug u back in, so we get negative e to the minus sine of x plus c, and that's equal to e to the minus sine of x times y. I'm just rewriting the left-hand side. So now all we have to do is divide the whole thing by e to the minus sine of x. You can see those cancel out. And so we get y is equal to minus e to the minus sine of x divided by e to the minus sine of x, which is going to just end up being -1, plus c divided by e to the minus sine of x. And we can move that to the numerator because we always just change the sign. So we get -1 plus c times the sine, oops, that's wrong, e to the sine of x. So let me just check that. Problem number 9, section 6.4. So the answer is -1 e plus c e to the sine of x. So that's correct. We are on problem number 12, chapter 6. And it's just another one of these integrating factor problems. It's first order linear differential equation. So let's just write it down. So we have y prime plus 3y equals e to the 3x. Now, if you take a differential equation class, you would know that the solution has to have the form y equals something e to the 3x for that to work out. But anyway, so that's probably what it's going to end up being, and there'll be some constant, arbitrary constant term. Okay, so but we don't know that right now. So what we do is we look at it standard form. So that's the first question. I need to set the default of this thing so it's not so big. Okay, standard form. So standard form means you have y prime with no coefficient except 1 in front. So that's okay. We have the y stuff by itself on the left-hand side, and then we have all the other stuff on the right-hand side. So in this case, our original equation is already in standard form. Identify p of x and q of x. So p of x is the coefficient in front of the y. So p of x in this case is equal to 3, and q of x is just what's on the right-hand side, e to the 3x. The next thing is to calculate the integrating factor. So as long as it's a first-order linear differential equation, we can use the integrating factor approach. And because this is not squared and this is not squared, so anything involving y is not squared, then it is linear, and it's first order because we just have the first derivative. So the integrating factor, we just say u, which we call u of x, is equal to e to the integral of p of x dx. So we just substitute in p of x, so we get e to the integral of 3 dx. And the integral of 3 dx is equal to e to the 3x. So this constant comes out of the integration. The integral of dx is just x. So then you get 3 times x. We don't have the arbitrary constant because we never do that with integrating factors. We just need a solution. There's no b solution. I could add a constant in there and I think it would be okay, but we don't. Okay, so that's the integrating factor. This u of x is the integrating factor. So that's what that's called. And remember, the integrating factor is a factor that we can multiply every term in the original differential equation by, so that we can collapse these two into a single derivative of a product. So the next thing is we multiply the differential equation by u of x. That means everything. So I show that as the integrating factor is e to the 3x times the whole differential equation. So everything. So this is going to be applying the distributive property. So what we get is e to the 3x times y prime plus 3e to the 3x times y is equal to e to the 6x. And that's because these are obvious because you're just multiplying it out. Here, e to the 3x times e to the 3x, you add the exponents, so you get e to the 6x. Okay, now, this, because of the way we calculate the integrating factor, we can say that this is equivalent to e to the 3x, which is this term, times the term here, just the y part, prime. And what that means is if we take the derivative of this product, we take the first term times the derivative of the second, plus the second, plus the derivative of the first term, which derivative of e to the 3x is 3e to the 3x, so that's that part times the second. So that's just, this is a product, this is the result. So then we can integrate both sides. And this derivative is with respect to x. So we can basically take this, multiply by dx on both sides. Why is that the case? Well, e to the 3x y prime is the same as d dx of e to the 3x y. And so if we then change that into differential form, it will be d e to the 3x y divided by dx, and then we multiply both sides by dx, and we get that, and then we can integrate it. Okay, when we integrate this, we just end up with that product. So this left-hand side integral becomes e to the 3x y. The right-hand side, well, the integral of this e to the 6x, let's just do that separately. We'll do that. So what I'm going to do is I'm going to move this down, leave a little room to do this part here. Because if the answer is going to be 1/6 e to the 6x, but if you didn't know that, what we would do is we would say u is equal to 6x. So that'll make this into e to the u. And then we calculate du, which would give us 6 dx, or dx is equal to du divided by 6. So I'm just solving for dx, and I can make this substitution into there. That integral becomes e to the u times du divided by 6. Factor the 6 out. 1/6 e to the u du. And the integral of e to the u du is just e to the u. So we get 1/6 e to the u plus c, of course, plus c. Substitute u back in. So we get 1/6 e to the 6x plus c. So that's the integral. The quick way would be to say, okay, I know that I'm going to divide by this coefficient. So I take 1/6, and so I divide by the derivative of this thing, basically. And so I divide by 1/6, and I know the integral e to the 6x. I just make it e to the 6x. So you could do it quickly if you're so inclined. So now we can rewrite the right-hand side as 1/6. So let me change my pen here. So what we get is 1/6 e to the 6x plus c. And then to solve explicitly for y, we're going to divide both sides. Or, well, let's do it two ways. So you could, there's two things you could do, whichever one you want to do. So one way is to multiply by e to the minus 3x. That would be one way, because when you multiply e to the 3x times e to the 3x, you add the exponents, and you get e to the 0, which is 1. And then you'd end with y. That would be one way. Or we could divide by e to the 3x. So we put a big line here, do the same. So it's the same thing here, so maybe it might be easier to do that. So this just becomes y, and we get 1/6 e. Well, we have 6x minus 3x, so you add the exponents, you get e to the 3x plus c divided by, or not c divided by, but just c multiplied by c. So we get to c, that's not x, that's multiplying. Let's put that as a dot, just to make sure we're clear. So we're multiplying it by that, so you get c e to the minus 3x. And that should be the final answer. So let me look in the book. Y is equal to 1/6 e to the 3x plus c e to the minus 3x. Okay, so now we're doing problem 18. So let's read, where are we? Okay, so really it's the same thing, except the first three problems we did were finding general solutions to the linear differential equation. And here we're finding the particular solution. So we have to find the general solution and then apply the boundary conditions in this case, which is like initial conditions. So we get x cubed y prime plus 2y is equal to e to the 1 over x squared. Okay, this is not in standard form because we have this x cubed here, so that's the first thing we're going to do, standard form. How do we get that? Well, we're going to divide by x cubed. So we divide everything by x cubed. So when we do that, the derivative part becomes just 1 times x prime. And then we get 2 divided by x cubed y is equal to e to the 1 over x squared divided by x cubed. Okay, so now we are in standard form. Okay, identify p of x and q of x. Yeah. In reality, we don't really need to identify q of x. It just becomes part of the solution. It's a little different than the way the book does it. I like this way better. Okay, so we can do p of x. So p of x is equal to 2 over x cubed. So then we calculate the integrating factor. Calculate integrating factor. And we can do this because, again, this has to be a first order linear equation. Okay, so next step is to calculate the integrating factor. So, as usual, I really need to change that default. I just did that one day. Okay, u of x is equal to e to the integral of p of x dx. And if you remember, I guess it was, well, it depends on when you watch this video, but you know, I said that first order differential equations usually have some solution that involves e to the x. And you can see that happening here, that the whole procedure involves finding e to the x, or involves e to the x. So, okay, so now we plug it in here. So we get e to the integral of 1 or over 2 divided by x cubed dx. So let's do the integration part separately over here. So what is the integral of 2 over x cubed dx? That's the same as the integral of 2x to the minus 3 power dx. So when we integrate, we add 1 to the exponent. So we'll get x to the minus 2, and we divide by the new exponent. So this is the constant, and this is the new exponent. Those match up. So you see we have 2 divided by 2, so we get negative x to the minus 2 power. We don't add our arbitrary constant because we don't do that with the integrating factor. So u of x is equal to, our integrating factor is equal to e to the negative, well, this is x squared, 1 over x squared. So let me rewrite that. This is the same as negative 1 over x squared. So anyway, that's our integrating factor. It's not surprising that it matches up this pretty closely. Okay, let us go ahead and I'm going to keep on this page just because I want to be able to see everything. So now we're going to multiply the differential equation by u of x. So we have e to the minus 1 over x squared times the differential equation. So that's our differential equation multiplied by the integrating factor. So what we get on the left-hand side is e to the minus 1 over x squared y prime plus 2 over x squared e to the minus 1 over x squared times y. And on the right-hand side, we have e to the minus 1 over x squared times e to the 1 over x squared. So when you add this exponent to that exponent, you get e to the 0. So the right-hand side just becomes 1 over x cubed. And that works out good because I can integrate that. Okay, this side becomes, you can collapse it. It becomes this term times that term. And something's bothering me here. No, it's okay. Yeah, because this will give me a negative. When I move this to the numerator, it'll be x to the minus 2. When I take the derivative, I'll get x to the minus 3, but I'll multiply by negative 2. So the negative times positive gives me a positive. So that does work out, right? So we have the quantity. We get the quantity e to the minus 1 over x squared times y prime is equal to 1 over x cubed. Now we integrate both sides and multiply by dx and integrate. Okay, so the left-hand side just becomes e to the minus 1 over x squared times y. The right-hand side becomes this integral. This is the same as x to the minus 3 power dx. We add 1 to the exponent. We divide by the new exponent. So, and then to solve, we solve for x, solve for y, sorry. So how do we do that? Well, we multiply by e to the plus 1 over x squared. Because if we do that, this one will have e to the plus 1 over x squared plus negative 1 over x squared. So these go to 0. So that's multiplying. It's called dot. So what happens is the left-hand side just becomes y. On the other side, we get negative 1 over 2x squared, because I'm going to move that to the denominator, times e to the 1 over x squared. So let's just rewrite that. Y is equal to e to the 1 over x squared divided by 2x squared. Oh, I forgot my c plus c. Oh, actually I need to go back here. I forgot c earlier. So this should be plus c. This should be plus c times e to the 1 over x squared. And so we get plus c times e to the 1 over x squared. That was problem number 8. And we haven't finished it completely, but let me just check it to this point, because we have to apply the initial condition. So I get e to the 1 over x squared times, yeah. Oh, here it is. Next. Yeah, they do a little bit of simplification here, so let's just do that. So if we factor out e to the 1 over x squared, what's left is negative 1 over 2x squared plus c. And then we can combine these two by finding a common denominator, which is going to be 2x squared. So what we'll get is we'll get negative 1 over 2x squared plus c times 2x squared divided by 2x squared. So you can see I've multiplied the numerator and the denominator by 2x squared. And then I can combine these two. So I just add these. So I get y is equal to e to the 1 over x squared. Just checking something out here. Okay, that's what they did. And I'll get 2x squared c, but I can combine the 2 times c is just another arbitrary constant. So this part, 2c, just becomes a new c, which I'm not going to give a different name to it. Cx squared minus 1 over 2x squared. Okay, so that's right. Now we apply the initial condition. So that is our general solution. So the initial condition is y of 1 equals e. And what that means is when x equals 1, y equals e. So we plug that into this equation. So y is equal to e. We get e to the 1 over 1 squared times c times 1 squared minus 1, all divided by 2 times 1 squared. So for x I put in 1, and for y I put in e. So we get e is equal to e to the, that's e to the first power, which is just e. And then we have c times c, we see c minus 1 divided by 2. Okay, 2 times 1 squared is 2. Okay, so I have to solve for c. So what I'm going to do, I'm going to multiply both by 2. So I get 2e is equal to e c minus 1. Distribute the e. So I get c times e minus e. So that becomes c times e, and e times negative 1, which is negative e. I add e to both sides, so I get 3e is equal to c times e. The e's cancel out. I get c is equal to 3. So my final answer, which is the particular solution, is y is equal to e to the 1 over x squared times the quantity 3x squared minus 1 over 2x squared. And that is the correct answer. Okay, we're on problem 27. And 27 is a Bernoulli equation, so let me write that down. So this is a little bit more complicated than the first order linear differential equations. So what we're doing is we are going to take this and do some substitutions to convert it into a differential equation that becomes first order linear. So it's kind of like we'd use substitution. We choose the appropriate substitution. So the original equation we can't solve, but then we can. And usually what you do is you look for the term on the right hand side and you see what that is, and then you multiply the whole expression by e to the minus 2 power, or divide by e squared, because that will be the way you solve it. If you just looked at the left hand side, you'd say it's first order linear differential equation, but then you have y squared here, which makes it nonlinear at this point. So to solve nonlinear equations, you have to find some substitution so that you can change a linear equation into a nonlinear equation. So what we're going to do is we're going to multiply by 1 over y squared. So multiply everything. So you get what you get is you get y prime divided by y squared. Excuse me. 1 over x times y divided by y squared is equal to x. Okay, so if you multiply by 1 over y squared, that just becomes x. So the substitution, I've forgotten. I've done these for a while. Okay, z. So basically, we're going to let z equal, well, not yet. We're going to look at this thing. So that really becomes y prime Okay, so this becomes y prime over y squared plus 1 over x times 1 over y is equal to x. Okay, so y divided by y squared is just 1 over y. So what we're going to do is we're going to let z equal 1 over y. Okay, because normally we have no constant times yes, okay, I'm trying to remember, make sure I'm doing this right. Yes, that's correct, okay. So this part's going to be z. So if we took z prime, this is 1 over y is the same as y to the minus 1 power. So when you take the derivative of this with respect to x, what you'll get is negative 1 times y to the minus 2 power, which is the same as negative 1 over y squared times y prime. Okay, so that I should have had that first part. So this is times y prime. Okay, because it's an implicit differentiation because this is y with respect to x, so I have to have this implicit term on the end of it. So now I can make these two substitutions in. So this is my first attempt since I haven't done it for a year, so I don't remember all the steps exactly, but I'm getting there. Okay, so what we know again is that z is equal to y to the minus 1 power, or 1 over y. We know that z prime is equal to negative 1 over y squared. Well, it's y prime over y squared. Okay, so you can see what I have here is actually have, this is equal to, so y prime over y squared is equal to negative z. So if you multiply both sides, z prime. So going back here, the first term becomes negative z prime. The second term becomes, well, 1 over y is equal to z. So you get plus 1 over x times z is equal to x. And if we multiply both all terms by negative 1, we get z prime minus 1 over x. Z is equal to negative x. So now this is the transformed equation, and the in terms of the variable z, it's a first order linear differential equation because I just have z prime and z. I don't have z squared like I did in the original equation where I have y squared. So what I'm going to do is I'm going to solve this by integration by using integrating factor, and then when I finish, I'll make the substitution back in. So that's kind of the way it works. So it's in standard form now. So next thing I do is find p of x, which is negative 1 over x. The integrating factor is going to be equal to e to the integral of p of x dx So I get e to the integral of negative 1 over x dx. I factor out the negative sign, so I get e to the minus natural log of the absolute value of x. And if I move the negative sign in to the natural logarithm, which I have to do so I can use the properties of logarithms, the inverse properties of logarithms and exponential functions, so I'll get 1 over the absolute value. This becomes x to the minus 1 power, which is the same as 1 over x. So when I use the inverse relationship between exponential logarithms, this just becomes 1 over x. Again, I take away the absolute value sign. So that's my integrating factor, 1 over x. So let me go ahead and multiply it by it. So what I get is integrating factor times the differential equation in terms of this new variable z. So there's my integrating factor multiplied by my first order linear differential equation. And so I get 1 over x z prime minus 1 over x squared z is equal to negative 1. Now I'm going to collapse those. So this becomes 1 over x times z, the whole thing prime. And this just becomes negative 1. I multiply by dx. So this just becomes this times dx integral. This becomes negative 1 times dx, which is negative dx integral. So the left-hand side just becomes 1 over x times z, and the right-hand side just becomes negative x. The integral of negative dx is negative x. We add our arbitrary constant c at that point, and then we can multiply by x. So multiply by x. That just becomes z on the left-hand side. So we get z is equal to negative x squared plus c times x. So we solved the first order linear differential equation in terms of z, but z is equal to 1 over y. So if we plug that back in, now we have 1 over y is equal to negative x squared plus cx. So y is equal to 1 over negative x squared plus cx. Or y is equal to 1 over cx minus x squared. So that should be the answer. Let's see what we get by looking at the answers. That was number 27. Y is equal to 1 over cx minus x squared. Excellent. So let's go back and do this whole thing over again. There's a lot of parts to it. The original differential equation was not linear, but we can make it linear by multiplying both sides by 1 over y squared, which will get rid of this. So if you multiply by 1 over y squared, you get everything here divided by y squared, basically. So you get y prime over y squared plus y over x times y over y squared is equal to x times y squared divided by y squared, which is 1. Okay, what did I do next? I'll clean this up, so I was able to cancel that out. I let z equal this part right here. Z is equal to 1 over y, which is negative y to the minus 1 power. So if I take the derivative, z prime, I get negative y, negative from this here, this exponent, negative 1, y to the minus 2, because I've decreased the exponent by 1. I have to do it implicitly, so I include a y prime at the end of it. If it was x, then I wouldn't, but because it's implicit, I have to do that. So, and I changed y to the minus 2 power is equal to 1 over y squared. Then I go back to the original differential equation, and I can make these substitutions. So this is negative z prime. This is equal to z, and I get that. And now what was nonlinear becomes linear in terms of z. I put it in standard form. I calculate the integrating factor by identifying p of x. So I got that, my integrating factor. I multiply everything in the z equation by the integrating factor. As a consequence, I can take these two terms, make them into one term, which is this times that. You can see if I take the derivative of 1 over x, I'll get negative 1 over x squared. If I take the derivative of z, I get z prime. So then I can multiply both sides by dx, integrate both sides. The left-hand side just becomes the term in the parentheses. The right-hand side just becomes negative x plus c. Multiply both sides by x to get z by itself. So this becomes z, this becomes x squared, this becomes cx. I then substitute z, which I had back a couple of pages back, as 1 over y. So z becomes 1 over y. Therefore, y is just the reciprocal. If I take the reciprocal of this, I take the reciprocal of that, which is 1 over that quantity. And then just rearrange this so the positive term was first and the negative term was second. It's just a little better for clarity. Okay, sorry for the delay there. I was thinking about something else. Anyway, I'm back to doing these Section 4 homework problems. The last one I did was 27, which is a Bernoulli equation. So we're going to go to 35. And 35 and 46 are not Bernoulli equations, they're word problems. So they're actually usually easier. It's just a matter of kind of digging through all the stuff to figure out what's what. So let's just read it. When predicting population growth, demographers must consider birth and death rates as well as the net change caused by the difference between the rates of immigration and emigration. Let P be the population at time T, and let N be the net increase per unit time resulting from the difference between immigration and emigration. So the rate of growth of the population is given by this differential equation. So that's the key thing here. And what we're trying to solve for is the population is a function of time. And we're assuming that actually, what are we solving for? Oh, I'm writing the wrong, went to the wrong problem here. dp dt is equal to k times p plus n. So this is due to population. This is due to birth and death rates. And that constant k, if it's positive, then you're increasing the population because of more births than deaths. If there's more deaths than births, then it's negative. K is negative. N is the other factor, which is people moving to the place or moving away from the place. They're not dying or being born, but they're moving. And that we're assuming that there's a fixed amount, it's a fixed difference. So if you're in the United States, there's probably a net N is probably positive from just normal immigration. More people come into America than leave America. But if you were looking at Ireland during potato famine, this would be a negative thing because probably nobody's coming to Ireland. Everybody's trying to get out. Okay, solve this differential equation to find p as a function of time if at time t equals 0, the size of the population is p0. So that's our differential equation. Our initial condition says that p, we'll call p0, which is the population at time t equals 0. So we could say that when t equals 0, which is the independent variable, p is equal to p0. So that's another way of writing that. So what is this? This is let's make dp dt p prime. So it's p prime is equal to k times p plus n. Now you can't just do separation of variables because if we multiplied by dt, we'd have p times dt, so they're not decoupled. So you end up having to you have to identify it as a first order linear differential equation, which means we can use integrating factors to do that one. So from this point, we put in the standard form. So at this point, the rest of it is just math. So standard form would say p prime minus k times p is equal to n. So it's standard form because this is a 1. We have p and p prime. We don't have p squared or p prime squared. So that means it's linear. We only have p prime, which means it's first order. So that means we can use the integrating factor approach. So the integrating factor, p is a population. So let's use some other letter. Let's call it, we'll say w of x is equal to minus k. That's the coefficient in front of the p term. So u of x, in this case, using our terminology, is equal to e to the integral of w of x dx. And so that's e to the integral of minus k actually it's dt, w of t, because it's time is the independent variable in this case, not x. Okay, so w of t dt. So w of t was just minus k. So the integral of that is e to the minus kt. So there's our integrating factor. So we take the original differential equation and we multiply every term by this integrating factor. So we get e to the minus kt p prime minus k times e to the minus kt times p is equal to e to the minus kt times n. Okay, we can collapse that one down to e to the minus kt, which is this term, times p. And that's, taking the derivative of that, that's equal to e to the minus kt times this constant n. Multiply by dt and integrate. I'm going to put the constant out in front. Okay, the left-hand side just becomes e to the minus kt times p. The right-hand side becomes n, which is a constant, so we leave that outside. The integral of e to the minus kt is equal to e to the minus kt divided by negative k. And we add our arbitrary constant c. Okay. Again, I'm not going to do this every time because if it was e to the kt, the integral would be 1 over k e to the kt. If it's negative, it's the integral of e to the minus kt is minus 1 over k e to the minus kt. And you see it works out. If we take the derivative, you'll get the derivative of e to the minus kt is negative k e to the minus kt. When you have negative k divided by negative k, it becomes 1. So you get back where you started. Okay, so what do we do now? Well, we want to get p by itself. That's what we're trying to solve for. So we're going to multiply by e to the kt. So we multiply everything. So what happens? E to the kt times e to the minus kt, add the exponents. That goes to 0, so you get e. This results in e to the 0, which is 1. So you just get p. Same thing happens here. So you get negative n over k. And then you get c e to the kt. So this is the general solution. So it's a solution with one arbitrary constant, which is not n. N is a constant, k is a constant, but c is the arbitrary constant. And I'm just getting the answer to make sure I have done everything correctly. C e to the kt minus n over k. Okay, so that's good. So now we apply the initial conditions. So what the initial condition says, when t equals 0, p equals p0. So for p, we put in b0. The first term is not affected by the value of t, plus c e to the k times 0. So e to the 0 is 1. So we get p0 is equal to minus n over k plus c. And if we solve for c, it's going to be equal to p0 plus n over k. So now we plug that back in, so we get p is equal to minus n over k plus c, which is p0 plus n over k times e to the kt. And I think we can rearrange this. What we're going to do is we're going to, we don't know that, is it? p0 plus n over k e to the kt minus, well, we'll just put, all I'll do is put the positive term first, p0 plus n over k e to the kt minus n over k. And so that's your solution, that's your particular solution to the differential equation. Because the arbitrary constant has been replaced by this. Okay, last problem, 46. Actually, I don't think that's right. Must be 40. Yeah, 40, 46. So let's read it. It's on page 439. The management at a certain factory has found that the maximum number of units a worker can produce in days is 40. The rate of increase in the number of units N produced with respect to time T in days by a new employee is proportional to 40 minus N. Determine the differential equation describing the rate of change of performance with respect to time. Solve the differential equation. Find the particular solution. So here they don't actually give you the differential equation. You have to kind of figure it out. So let's think about this. So the maximum units a worker can produce is 40 a day. The rate of increase in the number of units is produced with respect to time. The rate of increase, so that means D, what do we want to call it? I guess P is good enough as anything. dP dt, the rate of increase, or the rate of change, in this case it's increase, is the rate of increase in the number of units N produced with respect to time by a new employee is proportional. So when it says proportional, we have some constant of proportionality, and we multiply it by 40 minus N, where N is actually, that's the variable, is N. So the rate of change initially is K times 40 when N equals 0. And then as you get closer to 40, the rate of change the rate of increase gets smaller, because that's the way everything works. When you learn something, you learn a lot to start with, and then you learn less as you go along, if you're trying to master a task. And so another way of saying it would be the rate of change is equal to a proportionality constant times the difference. But in this case they say it's proportional, which means we put K in there. So what we want to, let's call this N prime. dN dt is N prime. And we're going to multiply this out. So we're going to have K times 40 minus K times N. And we want to see if we can rearrange this to look like a first order linear differential equation. So if we add Kn to both sides, and we keep the other thing 40K on the other side, now we have a first order linear differential equation for N. And so we got N prime and a constant. It doesn't have to be a constant, but in this case it is. So it's very similar. If you look at 35, really it's pretty much the same kind of deal, except this has another term, but it's still a constant. K is a constant based upon how quickly people learn. Okay, so there we go. That's our first order linear differential equation. What else do we know? Well, to find the particular solution, we're going to say find the particular employee for a particular solution for a new employee who produced 10 units at the first day and 19 units on the 20th day. So for this is with respect to time, so T equals 0, or T equals 1, I guess, really. Okay, let me find my pen here. So T equals 1 day, N is equal to 10, and T is equal to 20, N is equal to 19. So one of these is going to figure out this K, and one of them will figure out what the arbitrary constant is once we do this differential equation. Okay, so we'll use this in the third part of the problem. But first two, this is part A. Here's our differential equation. Part B, solve the differential equation. Okay, since it's a first order linear differential equation, we're going to use integrating factors. So P of x is equal to k. That's this coefficient right here. So the integrating factor is equal to e to the integral of P of x dx. So we have e integral of k times, and it's actually t, dt. So the independent variable is t. So we have k, which is constant with respect to time, times dt. So you get e to the kt. So that's our integrating factor. Take your differential equation over here, multiply the whole differential equation by the integrating factor. So we get e to the kt n prime plus k e to the kt times n is equal to 40 k e to the kt. Collapse that down, e to the kt times n, whole thing prime, equals 40 k e to the kt. We integrate, multiply by dx, integrate. Multiply by dt. The left-hand side just becomes e to the kt times n. The right-hand side, 40 is a constant, k is a constant. So then we have the integral of e to the kt, which is e to the kt divided by k. If it had been e to the minus kt, the answer would be negative e to the kt over e to the negative kt over k. So that's the only difference. We're going to multiply by e to the minus kt. So when we do that, this will just become n. This will just be, the k's cancel out, so you get 40. So that cancels out. E to the kt minus e to the minus kt is 1 plus c e to the minus kt. So c times that is that. So that's our general solution. And this is problem number 40, so just let me check here. So n is equal to 40 plus c e to the minus kt. Okay. So the last case is applying the initial conditions. So what we said, the first one was for t equals 1, n equals 19. So what do we do? Well, here's the equation. So 19 is equal to 40 plus c e to the first power. So if we subtract 40 from both sides, you'll get negative 21 is equal to c e. So c is equal to negative 21 divided by e. Oh, I'm doing something wrong here. For t equals 1, n equals 10, so that's wrong. Yeah, let me fix that. So, okay, so we had, this is 10. So 10 is equal to 40. Oh, and I forgot something here too. Oh, yeah, k. So t is equal to 1, so we get, there we go. So 10 is equal to 40 plus c e to the minus kt, and it's minus k. So how do we solve for that? Well, you could subtract 40 from both sides, so you get c is equal to, well, e to the k minus k, so c is equal to negative 30 divided by e to the minus k, or it's equal to negative 30 e to the k. So that would be the arbitrary constant c. So we'd stick that back in, and you get n is equal to 40 plus c, which is negative 30 e to the k times e to the minus kt. Okay, 40 plus c, which is negative 30 e to the k times e to the minus kt. Or n is equal to 40 minus 30e to the negative k times t minus 1. So what I've done is I've added these two. So you have k minus kt, and just factor out a negative k, you get t minus 1. Okay, the second condition says that when t is equal to 20, n is equal to 19. So let's plug that in. So we get 19 is equal to 40 minus 30 e to the minus k times t, which is 20 minus 1. So if we subtract 40 from both sides, we'll get negative 21 is equal to negative 30 e to the minus k times 20 minus 1. If we divide by negative 30, we'll get that e to the minus k times 20 minus 1 is equal to negative 21 divided by negative 30, which I need to get my calculator up for this part. Okay. So 21 divided by 30 is 0.7. So 0.7. Okay, then what we do is we take the natural log of that side. So they have natural log of e to the minus k times 20 minus 1 is equal to the natural log of 0.7. So the natural, well, the right-hand side just becomes negative k times 19, basically 20 minus 1. And the right-hand side becomes the natural log of 0.7, which is negative 0.357, rounded off. So k is equal to negative 0.357 divided by negative 19. K is equal to negative 0.357 divided by negative 9. Wait a second. Negative 0.357 divided by negative 19 is 0.0188. So what we get for the almost final answer is that n is equal to 40 minus 30 e to the minus k, which is 0.0188 times t minus 1. But that's not quite, that's correct, but what we have is 30 times e to the minus 0.0188 t times e to the plus 0.0188, because negative here times negative is positive. So this e to the 0.0188, so that's e to the 0.0188 is 1.0189. So this here is equal to 1.018, actually 1.019. So 30 times that number is 30.5685. Actually, it's not exactly that, but the book is slightly different just because we rounded off. So you have 40 minus 30.57 e to the minus 0.0188 t. So that's the correct solution. I'm just going to, the book does it slightly differently. What do they do? What they do is the first equation they solve using the first initial condition. You get negative 30 is equal to CE to the minus K. So that's from the first initial condition. Then the second one, when they apply the second one, you get this equation. Negative 21 is equal to CE to the minus 20K. And then what they do is you divide them out. So you take negative 30 divided by negative 21 is equal to CE to the minus K divided by CE to the minus 20K. So these cancel out. And so 30 divided by 21 is equal to 1.428 is equal to, so we have e to the 19K. Why is that? Because when you move this up here, it becomes 20, positive 20K, and you add 20, then subtract 1 from 20, you get 19K. And then we do the same thing. You take the natural log of both sides. Natural log of 1.428 is equal to the natural log of e to the 19K. So you get 19K from this side. You take the natural log of 1.428. You get 0.356, and you divide that by 19, and you get 0.0188, which is exactly what I got. It's just a slightly different way of coming to the same solution.